In this last section, I'm going to start out slow and then I'll end with a bang. So you may not like the ending, but let's look at a problem that are what I call mixed constraint problems. This first problem says an individual on a high protein, low carb diet requires at least 100 units of protein and at most 24 units of carbohydrates. The diet will consist entirely of 3 special liquid diet foods, A, B, and C, and the contents and cost of the diet foods are given in the table. How many bottles of each brand of diet food should be consumed daily in order to meet the protein and carbohydrates requirements at a minimal cost? Okay, so down here you can see that we have 3 types of liquid foods, A, B, and C. Now, food A has 10 units of protein per bottle, B 10 units of protein per bottle, and C 20 units of protein per bottle. A has 2 carbs per bottle, B has 3 carbs per bottle, C has 4 carbs per bottle. And then A costs 60 cents a bottle, B costs 40 cents a bottle, and C costs 90 cents a bottle. So I'm just going to let X1, X2, and X3 represent the number of bottles of brand A, B, and C that are consumed. Well, we know we want to minimize the cost, so the cost would simply be just the cost of each bottle times the number of bottles consumed. So the cost we want to minimize, so make sure we identify where we're minimizing or maximizing. Cost equals 60 cents or 0.6 times X1 plus 0.4 times X2 plus 0.9 times X3. That'll be the total cost based on this last row, cost per bottle. And now if we have to have at least 100 units of protein, then the amount of protein must be greater than or equal to 100. And let's look where you get the protein from. You get 10 units of protein per bottle A, 10 units of protein per bottle B, and 20 units of protein per bottle C. So the coefficients here would be 10x1 plus 10x2 plus 20x3, and that's your total protein. So set that greater than or equal to 100. Now the carbs say just the opposite. The carbs say at most 24. So at most means you have to have less than or equal to. So when we do the carbs, we'll use less than or equal to. So let's see where we get our carbs from. We get 2 units from bottle A, 3 units per bottle B, and 4 units per bottle C. So 2x1 plus 3x2 plus 4x3 is less than or equal to 24. And that's the original problem. Now, this is a mixed constraint problem, but then again, it's not. Originally, you see I have a greater than and a less than, but actually I could change that second constraint to greater than if I multiplied everything in this inequality by -1. And I'm not going to solve it or anything, but I just wanted to show you that you could do that. You might want to pause the video and read this and then restart it to hear my explanation on this problem. Basically what we want to do is we want to minimize the transportation costs, and we want to know how many students from each town should be enrolled in each school to meet these requirements. Now basically what you're doing is you've got basically 3 towns. I'll just kind of draw 3 little circles here. So you've got like 3 towns, towns A, towns B, and town C. And you're basically redistributing the students to 2 schools. So we'll let the rectangles be the schools. Okay, so basically the school district knows the cost. If you transfer students from town A to school 1, they know the cost is $4 per student. If you transfer them from town A to school 2, they know it's $8 per student. From town B to school 1, they know it's $6 per student. and from town B to school 2, $4 per student. And then from town C to school 1, it's $3 per student, and town C to school 2, it's $9 per student. So basically, we want to minimize the cost of transportation. So if we let X1 and X2, so let's say X1 represents the number of students that go from town A to school 1, and X2 is the number of students that go from town A to school 2, then that takes care of those students. Now, what about from town B? Town B to school 1, we'll call that X3, and we'll say the number that go from town B to school 2, we'll call that X4. And then the number that go from town C to school 1, we'll call that X5, and the number that go from town C to school 2, we'll call that X6. And now, since we know the costs, we can go ahead and put in our objective function, because we know we want to minimize the cost, but we know that it costs $4 to go from town A to school 1, so that's 4x1, $8 from town A to school 2, so that's 8x2, and then so on, $6, $4 for x3 and x4, and then $3 and $9 from town C, to school 1 and school 2, and so on. So there's your objective function. Now, this problem, hopefully you did read it. You saw that we know exactly the number of students in each town. We know town A has exactly 500 students. Well, if it has exactly 500 students, then the number of students that leave this, that get bussed out of here, must equal 500. Well, that would be x1 plus x2. It has to equal 500. You can have equal to constraints, as you see here. And since town B has 1,200, then the students leaving that town must equal 1,200. So x3 plus x4 has to equal 1,200. And then town C has 1,800 students, and so the total number of students leaving town C has to equal 1,800 students. So we're using equal to because if we use less than, then we're leaving a student behind, and there's no reason to use greater than if we know that's exactly the number of students we have. Okay, so that gives us our first three constraints here in the problem. All right, now a couple of other constraints has to do with the capacity of the high schools. Both of these schools can hold no more than 2,000 students. So if you think about it, the students that are coming into school 1 are the ones from town A, which is x1, the ones from town B, which is x3, and the ones from town C is x5. So x1 plus x3 plus x5 must be less than or equal to 2,000. But if you look at the students coming into the school 2, that would be the ones coming from town A, which is x2, the ones coming from town B, which is x4, and the ones coming from town C, which is x6. So not only does x1 plus x3 plus x5 have to be less than or equal to 2,000, so does x2 plus x4 plus x6. Now, the other thing it says here, it says at least 40% of the total population must be enrolled in each high school. So I guess that's to keep them from all trying to go to a particular school. So what we're going to do is we're going to figure out what is 40% of the total. Well, 40% of the total, 40% of 3,500 is what we're talking about here. So 40% of 3,500 would be 1,400. So that means that the students going to school 1, which again is x1 plus x3 plus x5, has to be at least 1,400, and the students going to school 2 has to be at least 1,400. So that gives us our next two constraints. And then the last thing it says here, it says no more than 60% of the students in any town can go to the same high school. Well, there's 500 students here, right? And 60% of 500 is 300. So that means no more than 300 can go from town A to school 1, and no more than 300 can go from town A to school 2. So in other words, x1 must be less than or equal to 300, and x2 must be less than or equal to 300. Well, town B has let's see, what does it have? 1,200 students. Well, 60% of 1,200 is 720. So no more than 720 can go from town B to school 1, and no more than 720 can go from town B to school 2. So x3 and x4 must be less than or equal to 720. And then finally, town C has 1,800 students, and 60% of 1,800 is 1,080. So no more than 1,080 can go from town C to school 1 or town C to school 2. So x5 must be less than or equal to 1,080, and so must x6. So that's your final constraints there. And then don't forget your non-negative constraints, because none of your number of students can be negative, so all of those have to be non-negative. And that's how you solve or set up a mixed constraint problem. And you can see this is a very practical problem, but we're not going to solve it. We're just going to set it up. Again, pause the video and read this problem here. And then when you're ready, start it back up, and you can listen to my explanation. Basically, what we want to do here, this guy sells these birdhouses and he wants to maximize his profit, but there are certain constraints that have to be set up. So let's look at what we're going to do. We basically have 3 stores and 2 types of birdhouses. So we have home to roost houses that are going to go to store 1, and we have flying home houses that are going to go to store 1. So the houses, we're going to let x1 be the, I'll just call the roost houses. The roost houses are going to go to store 1, and the flying houses are going to go to store 1. So that's going to be x1 and x2. So the number of roost houses store 1 is x1, the number of flying houses store 1 is x2. And then the number of roost houses to store 2 is going to be x3, and the number of flying houses to store 2 is going to be x4. And then same for x5 and x6, but that's store 3. Okay. A few things we can come up with. First of all, if you read the problem, it actually tells you what he profits on each one. On the roost bird houses, which would be x1, x3, and x5, he profits $6. So $6 per x1, $6 per x3, and $6 per x5. On the flying home houses, he profits $2 each. So $2 for x2, $2 for x4, and $2 for each x6. Okay, now I don't have time to do this entire thing, but let me just share a couple things with you. He wants twice as many flying home to roost bird houses. Store 1 wants twice as many home to roost bird houses than flying home bird houses. So that means x1 must equal 2x2. Store 2 wants twice as many home to roost than flying home bird houses. So that means x3 must equal 2x4. And then store 3 wants an equal number of each type, so x5 must equal x6. And since there's store 1 has a space for no more than 20 birdhouses, then the total store 1 gets has to be less than or equal to 20. Store 2 has space for no more than 16, so the total that store gets has to be less than or equal to 16. And he must sell at least 9 birdhouses to store 3. So x5 plus x6 must be greater than or equal to 9. Now, if you put all that together, you get a bunch of constraints here. Now, if you actually were going to solve this problem, you always want to get your variables to one side of the equation or inequality. So you'll notice I wrote this over here as x1 minus 2x2. I wrote this as x3 minus 2x4. And of course equals 0, and I wrote this as x5 minus x6 equals 0. So that's how you would actually want to write the problem if you were actually going to solve it. But this is just another problem, and notice you've got mixed constraints here. You've got less than or equal to constraints, you've got equal to constraints, and you've even got a greater than or equal to constraints. So there's several different types of problems you can run into out there. One more video on the Big M method, and then we're done.